After learning how to find the regression line of y on x, I now want to look at the question, how good is my prediction? To what degree I can use a line to predict y when x is given. In order to answer this question, I'm going to look at how well related are the variables x and y. If we take a point of coordinates x1, y1, my question can be answered by looking at how close are x1 to the mean values of x and y1 to the mean values of y. And in order to do this, I'm going to look at the product x1 minus mean values of x. This is a product that we saw as well in the expression of the gradient of the regression line. So for all points in the first and in the third quadrant, this expression will be positive. For points in the second or fourth quadrant, the expression will be negative. If I add all these points, assume I have n points, and if the expression I get is positive, then to a certain extent I can claim that the majority of my points are in the first and third quadrant, whereas if my expression is negative, then they are in the second and fourth quadrant. In the first case, I will say that there is a positive correlation between x and y, because the line of regression will have a positive gradient, whereas in the second case, I will say that there is a negative correlation between x and y, and I expect the gradient of the line to have a negative value. Please note that the gradient of the line is not a correlation coefficient. It makes sense, then, in order to define how well related are the variables x and y, to consider what is the expected value of this expression. If here I would have all the points in my populations, what would be the expected value of this expression? We will therefore define covariance of xy being the expected value of x minus the mean of x, y minus the mean of y, where x is a distribution of the x values, y is a distribution of the y values. We will now add a simpler expression or an equivalent expression for the covariance of xy. We will now look for an equivalent expression for the covariance of xy, which was the expected value of we can pause the movie and try by ourselves to open the brackets and then use a property that the expected value of x plus y is the expected value of x plus the expected value of y for any distributions, for any variables x and y. Next, we can use the fact that the mean value of y is a constant, so it will go in front of the expected value, and the expected value of a constant is a constant itself. And let us remember that the expected value of x is denoted by x bar, the expected value of y is denoted by y bar. So we obtained that the covariance of xy is the expected value of xy minus the expected value of x times the expected value of y. So this was supposed to be. Yeah, so the covariance of xy is the expected value of xy minus the expected value of x times the expected value of y. Let us remember that the covariance was used to define how related the variables x and y are. And also, we remember that in the case when x and y are independent, then the expected value of xy is the expected value of x times the expected value of y. Therefore, if x and y are independent, the covariance of xy is going to be 0. Let us see how a diagram where x and y are independent would look like. In this diagram, the variables x and y are not correlated, so x and y are independent, and according to the previous slide, covariance of xy is 0. I would expect, therefore, to have the highest covariance when there is a linear dependence between the variables. This is like the perfect correlation. When my scatter diagram will show like a line. In this case, there is a perfect dependence between y and x, a linear one, and let us express it as y equals ax plus b. Assuming I have this relationship between x and y, in this case the covariance would be maximum, because it's a perfect correlation between the two variables. Let's see what happens with the covariance of x and y in this case. It's the expected value of xy minus the expected value of x times the expected value of y. Now I'm going to express y in terms of x. And I'm going to open the bracket. Okay, so in this case, the covariance of xy is the known formula. And we continue. Let's cross out this line and start a bit from the left. The expected value of and now I'm going to open the brackets. Okay, so I open this bracket and I'll continue. I see that these terms cancel, so I get a expected value of x squared minus expected value of x squared, surprise, a standard deviation of x squared. And now I can write it as standard deviation of x squared, standard deviation of y squared, because we remember that if x and y are related by this, the variance of y is a squared variance of x. Therefore, the standard deviation of y is a standard deviation of x. So a times the standard deviation of x gives me the standard deviation of y. No, sorry, I don't need those squares here. So it's just standard deviation of x times standard deviation of y. So this is going to be the maximum possible covariance. The maximum possible covariance in the case of the perfect linear correlation. So covariance of xy has its maximum value, sigma x, sigma y, and therefore its minimum value will be negative sigma x, sigma y. How are we going to compare different pairs of distributions? We need a similar concept, such as standardizing the normal variable, the normally distributed variable. So in a similar way, we'll bring all covariances on a single scale. And we will define rho, the correlation coefficient of being covariance of xy over sigma x, sigma y. We can see therefore that rho is between -1 and 1. This is a Greek letter rho. As we saw before, x and y are independent if and only if rho is 0. And there is a perfect correlation, a perfect positive correlation for rho equals 1 and a perfect negative correlation for rho equals -1. So these are the formulae that use for the covariance and the product moment correlation coefficient. Let's call it a correlation coefficient. Now, see, they are very similar and still different. Is if you want something similar as between any normal distribution and the standardized normal distribution. And if you look at the units in which the covariance is measured is the same as the units in which x and y are measured, whereas the correlation coefficient has no units. Also, because the maximum value of covariance is sigma x, sigma y, sometimes covariance is denoted by sigma xy. It's just a notation for the covariance. Just to test covariance of x and x are perfectly correlated. It's a particular case of our linear correlation before, is the expected value of x minus. And if we open the bracket, you can test and see that actually is sigma x squared, which is the variance of x. Whereas the correlation coefficient between x and x is variance of x, which we found before, over sigma x, which is 1, and it gives me a perfect correlation. However, when this is the theoretical correlation coefficient between the two distributions. It involves all the values in the two distributions. However, if we want to find or to estimate it, we will take samples. And for each sample, we generate the sample product moment correlation coefficient, which generally is denoted by the letter R. And a very last observation is that if we take rho, which is a covariance of xy over sigma x, sigma y, we see that we can write it as the expected value of which can be written as which is the expected value of zx, zy, which are the standardized scores. So they are written in terms of the values on the standardized normal distribution.